So we were doing tours on a graph. We saw this Eulerian circuit problem, Königsberg bridge example. So we showed that there is a Eulerian circuit if and only if every degree is even, which was not the case in Königsberg bridge. So that is a fast algorithm. Second tour is this Hamiltonian tour, which turns out to be a very different creature. So this is an NP complete algorithmic question. There are no fast algorithms except, so the only algorithm will be, how do you find a Hamiltonian tour? Yeah, you just try out all possible tours, which is extremely, it's even more than in a way n factorial. So this the definition was that you want to no, it's not more than n factorial, exactly n factorial. Definition was that you want to find a permutation of the vertices which goes through all the vertices, right? So basically you just have to try all n factorial possibilities which go from 1 to 1 and check that it's actually a Hamiltonian tour. So checking is easy, but finding is the hard part. That is n factorial. So there is no, the problem is that there is no good mathematical description criterion for this which can be tested, except some theorems like this Dirac's theorem we will do today. This theorem says that a simple graph without self loops on n vertices is Hamiltonian if every degree is big, where big is at least n by 2, which means for odd it means more than n by 2, n plus 1 by 2. Any questions? So how do you prove this? So suppose each is a graph with degrees at least n by 2, but there is no Hamiltonian, but it is not Hamiltonian. So there is no Hamiltonian cycle. Which means that we want to get to a contradiction. It will be proved by contradiction. So any ideas how you will do this? So there was this property that if you add edges, then if you keep on adding edges, then what will happen in the end? It will become a complete graph. So in that case, obviously it will be Hamiltonian, right? So there will be a point when if you add a single edge, any edge, the graph becomes Hamiltonian. So let's reach that point. So keep on adding edges. Till it is non-Hamiltonian. And so what will happen is that since you are adding edges, the degree will remain large everywhere, and the graph we are assuming remains non-Hamiltonian. any other edge you add, it will become Hamiltonian. So we are in that setting now. Call this graph G. Okay, so the property that it has is G plus any edge is Hamiltonian. I mean any new edge, of course. Okay, so we can then basically we can as well assume that the given graph was such that it's non-Hamiltonian, high degree everywhere, and if you add anything, it becomes Hamiltonian. Is this clear? So now what can you do with such a graph? Can you get a contradiction? So let us consider a non-edge. I mean, there has to be a non-edge. If there was no edge, then if there was no non-edge, then it means it's a complete graph. It cannot be non-Hamiltonian. So consider any non-edge, call it UV in the graph G, and what can you say about U and V inside G? Is there a Hamiltonian path? Is there a Hamiltonian cycle? So you know that there is no Hamiltonian cycle involving UV, but there is a Hamiltonian path. Is that clear? So this is vertex V1, this is vertex Vn, we are defining it that way, and there is a Hamiltonian path. Any non-edge U comma V has a Hamiltonian path. So this we are calling V1, V2, Vn, because otherwise what will happen is if there is no Hamiltonian path, then you could just add the edge UV and the graph remains non-Hamiltonian, right? So that cannot happen. We have assumed that anything new you add, it becomes Hamiltonian. So it means that because of this, we have found a Hamiltonian path, which is a very strong condition, right? We did not start with, we may not have started with that, but now we have this Hamiltonian path. And what you consider now is the following to get contradiction. Define neighbors of V1 and Vn as, so set S you define as those vertices Vi plus 1 which have an edge to U. So those i's such that U comma Vi plus 1 is an edge. And define T similarly, but there is a slight difference which is in the subscript. So it's those i's such that VIV is an edge. So the only difference between these two definitions is that, of course, one is for U, the other is for V. But there is another difference that if Vi plus 1 is a neighbor of U, then you are not putting I plus 1 in the set, you are putting I. Okay, you are putting the previous index. And if Vi is a neighbor of, is adjacent to V, then you are putting I. Is this clear? So we are looking at the vertices which are adjacent. And from this we'll get a contradiction. Because point is that the graph is highly, the degree is very high in this graph. Okay, so if you take these two vertices U and V, the degrees are respectively at least n by 2. Right, so in some sense this S union T should be a large set. It should contain everything. That is what will contradict. That is what will give the contradiction. So to finish that, the only thing that can trouble is if S and T have an overlap. So can they overlap? Suppose S and S intersection T has some I. Then what happens? If there is an I which is in both the sets, then it means that Vi is adjacent to V. As in that picture, I have used the same picture for this. Moreover, Vi plus 1 is adjacent to U. So from this, from this picture, can you deduce a contradiction to the properties of graph G that we assumed? Well, the graph will have a Hamiltonian cycle then, right? Because if this picture is true, then you can go from U to Vi, you can come to V, then from V you can go to, in the orange path, Vi plus 1, and from Vi plus 1 you can take the red path to U. Right, so that will then be a Hamiltonian cycle which will contradict its non-existence. So this means that G has a Hamiltonian cycle, namely go from V1, V2, take the orange route to Vi, then you shift to red, so you come to Vn, and then you shift to orange to you, so you take Vn minus 1, dot Vi plus 1, and then you shift to red to go to V1. Okay, so that's the contradiction. So the contradiction means that S and T are disjoint. Is that clear? So the way we have defined these sets, they are disjoint, and moreover, obviously their sizes are lower bounded by the degree assumption. So both are n by 2. So their union is n. I mean, it has to be at least n by the property, and so it's exactly n. Is it possible that it contains everything? S union T is 1 to n? Why not? Sorry? Right. No, but so you are now getting that S union T is everything. Is that possible? I claim that that is a contradiction. So it's a contradiction because there is an element which is not in the union, and that is 1. Do you see 1 in S? Right, since S is shifted, these i's are shifted, I plus 1 you are looking at. So actually 1 is there, then maybe n. Is n the n? If n is in S, then you will be talking about Vn plus 1, which will not exist. So n is not in S. Is n in T? Yeah, so for this we assumed a simple graph. So n is the element. So S union T has to be then 1 to n, as the degrees, I mean the sizes, they have to be at least degree, which is at least n by 2. Sorry? Yeah, it will not matter in these discussions. No. Till now, whatever I have written, it doesn't matter whether n is even or odd. And the contradiction comes from the fact that this n element is not in S union T, which means a contradiction. And here we have used that there is no loop. In particular, the loop v comma v. So n cannot be in S because there is no Vn plus 1, and n cannot be in T because that will be putting v comma v in the H set, which is not there. So S union T can be at most n minus 1, but the degree says that it has to be everything. And that is what gives you the contradiction. Hence, so it means what? What is the thing that we assumed is wrong? It means that this UV non-H doesn't exist. Which means that graph was actually Hamiltonian. So the original graph that was given to you, that itself was Hamiltonian. So H is Hamiltonian. Okay, this is the sequence of arguments. Is this clear? Any questions? Okay, so that is Dirac's theorem. There are many generalizations available for this theorem. but we will not go over all of them. Let us look at the conditions here. So what happens if the graph is not simple? Is the theorem true? What's an example? Sorry, not arrows. So suppose you have self loops available, then what self loops will do is they will artificially jack up the degrees, right? So here n is 3, n by 2 is 1.5. And the degree is everywhere you see 2. So then by Dirac's theorem there should be a Hamiltonian, the graph should be Hamiltonian, but it is not. Is that clear? So if you add loops, so then it actually disturbs this idea of there are many, the degree everywhere is high, because it's high simply because of these loops and not because of the inherent structure. More important condition to check is this degree being at least n by 2. Suppose it is not, then can you show Dirac's theorem? What's an example? Cycle. In a cycle, the degree is very less. It's just 2. Yes. No. Anyways, the cycle has the degree is low, but it's also Hamiltonian. So that is not a good example. I want an example where degree, if it is just below n by 2, it's non-Hamiltonian. Yeah. Did you have an answer? Okay, so answer is not very easy. It is actually k n comma n minus 1. This is the complete bipartite graph, right? So you have n vertices mapping to n minus 1. All the edges are there. So the thing is that degree everywhere is what? At least n minus 1. So in this degree is n minus 1, while the total number of vertices is 2n minus 1. So half of that is n minus 0.5. So this is just less than that. It is just minus half smaller than that bound. But still the degree is very high. It's almost n by 2. And is this Hamiltonian? This we discussed before, right? That this is it's non-Hamiltonian, because the vertices are different in number. Then you can show that there is no Hamiltonian cycle. So if you try to change Dirac's bound by even minus 0.5, then you have these counter examples. Okay, so that condition is, all the conditions are actually needed, which means that this method cannot study the graphs which are degree less than n by 2. But as you know, there are many graphs which have low degree, but they are Hamiltonian, right? So then there is no way to study them via these methods. But it is Hamiltonian. This Dirac theorem is tight. But it's not necessary. So what it is, it's sufficient. But it's not necessary. Instead of theorem, let me just say Dirac's properties. So these properties which Dirac has used to deduce Hamiltonian, that property is sufficient and it's also tight. If you change the property slightly, then it doesn't work. But it's not a necessary condition. So there are a lot of graphs which are still not covered. Okay, so that's a problem. It's not like Euler's theorem. Any questions? Okay, if no questions, then let's proceed to new properties. So we'll after the midsem we'll study a lot more properties. Now we can just start some things. They will be to do with the coloring of a graph or independent sets in a graph. Something called vertex cover in a graph, etc. So coloring, you have already seen some examples. So let us start with that. In fact, no, let us start with independent set first. Yeah. So these examples that you saw for coloring before, which was basically, say you have a map and you want to color the map, which are the states in India, say. The condition was that no two adjacent states should get the same color, and similarly in a graph, no two adjacent vertices should get the same color. So you want to color the vertices in a graph. So one basic question you can ask there is, what is the maximum number of vertices which get color 1 or color 2 or color 3 and so on, right? So what is the if many like vertices set S, out of all the vertices we get color 1, what is the property of the set S? No two vertices in S are connected, right? So this is what is called an independent set. So we'll study those. So biggest set of vertices which are monochromatic. That's called an independent set. It's a very fundamental object in a graph, and it provides you numbers about the graph. So obviously there are many examples. One example is, say you are looking at the relationship graph of friends. Relationship graph of people. So you can think of students, and then the graph basically shows which two students are friends. You draw an edge between UV. So in an exam, if you want that the examination hall should not contain any two friends, right? Because they cheat a lot. So what is the biggest hall you can accommodate? Or what is the largest number of students which can be seated in a hall, right? So that question is obviously a question of finding the maximum independent set, and so on. So you can think of practical examples where this appears. So let us formalize that. An independent set of a graph G is a subset S of vertices such that for all UV in S, UV is not an edge. Okay, so it is any set of subset of vertices which is free of edge is called an independent set. It's also called stable set. And so this actually gives you a number attached to a graph which is called the stability number. So stability number denoted alpha G is what? Is the maximum independent set size, is the size of a maximum. I mean, there may be many subsets of equal size that are maximum independent. So, but obviously their sizes will be the same, right? Because it's a finite vertex set, yes. Yeah, that's a. So is the size of a maximum independent set S in G. Okay, so that is alpha G. So if you are given a graph, a practical graph, I mean graph that came from some practical question, how fast can you find this number alpha G? So of course alpha G is minimum, it can be what? Minimum it can be 1, right? And maximum it can be n, which is the vertex number of vertices. So it is just a number between 1 to n. How fast can you find it given a graph? Simple to state question. but it's very difficult to find. Okay, because if it is somewhere between n by 2, then you have to check out of n vertices all possible n by 2 subsets, which is like 2 raised to n subsets, like n choose n by 2. So even for a 100 sized graph, this is, you have to go over 2 raised to 100 possibilities. So as happens many times in combinatorial questions, there is no fast algorithm known. This is the only known algorithm. Okay, so this is practically an impossible problem to solve. Although it's a very important problem, but there is no algorithm known in practice. So fast algorithm for alpha G. So what is known is again this NP completeness result. Maybe you will hear this term in TUC course. Is it in that syllabus? Theory of computing. Oh, it is next semester for you, yeah. So next semester you might get to know what NP complete problems are. So it is one of these. So if you solve this, then you solve all other problems in computer science, which are practically open. So there's thousands of problems reduced to this. Another thing to define is maximal independent set. What is the difference between maximal and maximum? No, so the difference is that this maximum is globally maximum, and maximal is that I just give you a set, and I say in the definition that if you add any other vertex, any new vertex in it, then it will not be independent. Okay, in other words, it's a maximal independent set is a subset of the vertices such that S complement any vertex V you pick there, it has a connection to S. So you cannot include it. Okay, so this is a local optima or maxima. It may not be global. Do you have an example when this happens? Is an independent set S where such that for all V in S complement V minus S, S comma V, or if you add V in S, is not independent. So why is this concept required? Do you have an example where it's maximal but not maximum? Yes, exactly. So example is this star kind of a structure. So this is 1, this is, let's say, 2, 3, 4, 5. So in this graph, what is a maximum independent set? Example? Or what is alpha G? Alpha G here is 4, right? but there is a subset which is much smaller than 4, and it is maximal independent set, which is, it's 1. Is there any other choice? Yeah, you can also take, you can actually take any subset which has 1. That will be, except the, yeah, this 2, 3, 4, 5. Anything else will work. So you can take 1, 2, or you can take 1, 2, 3. You can take 1, 2, 3, 4, and so on. So you have actually many possibilities which are maximal independent, but they are not global maxima. It's not maximum independent. It doesn't match the stability number alpha g. So this is needed. 1 and 5, yeah, that's, I spoke wrong. So then there is no option. We can also take just 2. No, we can't take 2. I think 1 is the only option then. This is unique. Yeah, so in this case, this center point is actually unique. Is the only maximal independent set, different from or smaller than alpha g. Other options you don't have. But prove this as an exercise. Okay, so recall the complement of a graph. So what you do here is vertices are the same, but edges you make edges non-edges, non-edges edges, right? So this is V comma E complement. And what is the number of edges in G complement? So what is E complement plus E? This is n choose 2, right? So this is the complement graph. And now you can compare these things that we have defined. Independent set, what happens to it when you look in the complement graph? Because the vertex set is the same. So if S is a independent set in G, what is it in G complement? It's a complete graph, right? So that is called a clique. A complete subgraph is called a clique. So an independent set S, independent set S of G means that in G complement, S is a complete graph. And obviously converse is true as well. So the complete subgraphs in a graph, they become independent sets in the complement. And independent sets in a graph become complete graphs in the complement. So that's the definition of clique. So clique S of graph G has all possible edges. Okay, so this is also called the clique subgraph. I mean, it's a subgraph. So a complete subgraph of a graph we'll call by a different term, we'll call it a clique. Any questions till now? So, yeah, let's see again. So, if you have to find an independent set in a graph, can you find this by a fast algorithm? It's trivial, right? You just take a vertex. A vertex is an independent set. So, this algorithm is trivial. Now, let's challenge you more. Can you find a maximal independent set by a fast algorithm? How? Well, the definition will give you an algorithm. You start with a vertex and you remove all its edges, right? And after that, in the remaining graph, if there is a remaining graph, then you pick another vertex there and repeat. So this will give you a maximal independent set. Unfortunately, that is not good enough because it may never give you the global maxima, it may never give you the maximum independent set, right? Because that, I am telling you, is a hard problem. If you don't believe, then prove me wrong. So, maybe just to do that exercise. Maximal independent set is easy to find. In a given graph. It's basically a single scan of the vertices. Okay. So idea here is just pick a vertex V, put it in the set S. Remove the edges of V from the graph and then repeat. Okay, so this S will hopefully, if there is a possibility, it will keep growing and it will grow to a maximal independent set. That you can prove. So the definition is basically an algorithm itself. It's an easy thing to implement. Related concept is that of vertex cover. So a vertex cover S is a subset of the vertices of the graph G such that it should achieve what? It should cover all the edges. right? So vertex cover is a subset that covers all the edges, which means that if you look at the list of edges one by one, every edge is incident on something in S. So how do you write this? Is a subset such that for all UV in the edge set, either U is in S or V is in S. Okay, this is the condition. Look at the list, look at the edges one by one, and you check that at least one of these should be in S. Then it's called a vertex cover. So how easy is it to find a vertex cover? As given in the definition. Exactly. So you just take V, so that is clearly a vertex cover. So let me challenge you more, since you can do these trivial things easily. Sorry? No, least you cannot do. That will again be, as you can guess, it will be NP complete, but something that you can potentially do, which is, let's say, double the least. Within 2 factor of the least, can you find a vertex cover? So if the least out of 1000 vertices is, let's say, 10, I am allowing you leeway up to 20. That's an approximate vertex cover. Yeah, I should define the least first. So least vertex cover of G is one where obviously size of S is the least possible, is minimized, and then the claim is that some approximation of this can be found, 2-factor approximation. How do you do this? Yes, that will be the smart thing to do, yeah. But is that a correct algorithm, or do you want to make it more precise? Just going over the edges and picking either one. Wouldn't it be better to actually pick both? I mean, you basically pick an edge as a whole and delete whatever is connected to, whatever is adjacent to U and V, and then repeat. So this is similar to the previous algorithm, except in that vertex cover we were picking a vertex. Now we'll pick an edge. So pick edge UV, and like that you form your edge set, let's call it T. You grow this and remove the same step, remove the edges of U and V from the graph. edges incident on U and V. And then repeat. Actually, I should have said S instead of T. I don't need T. We need vertex cover, right? So and grow this S. So it's very similar, except that you go over the list of the edges instead of vertices. So can you show that this is a two-factor approximation of vertex cover? How do you show that? That if your minimum, the least vertex cover is size m, then this algorithm will output size maximum 2m, not more than 2m. So do that as an exercise. It's very simple. So prove that the size of S when this algorithm stops, and it will stop because it's just a linear scan on the single scan on the edges. S will be less than equal to the least vertex cover size twice. So the proof idea is just that if you look at the definition of vertex cover over the edges, it picks at least one. So usually it will pick only one if you want to optimize. But instead of that, you are picking two. So it's just 1:2 choice. Just formalize that. Yeah, so up to two-factor approximation is easy. Now, if you want to optimize it any further, then you get into this big complexity theory hurdle, which is NP completeness. Okay, so beyond this simple algorithm, essentially nothing else is known how to solve this practically, and since it's NP complete, all other problems of computer science reduce to this question. Okay, which is not at all clear to you right now, but as you grow old, you will learn. So, better approximations are hard problems. Okay, so I mean, again, this is just conjectural because no one has proved that it's hard. It's just that everybody has proved that whatever problem they wanted to solve, it reduces to this. Okay, but it doesn't mean that this is inherently hard. I mean, it is not a mathematical proof. It's just that people are frustrated with their failure. So, what else is there? Yeah, so you have you've seen many problems now. This computation of stability number, maximum independent set finding, which is again believed to be hard. For the clique also, you can define the maximal clique problem or the maximum clique problem. Right, given a graph, what is the maximum clique inside, contained inside? So that again will be, it will again be hard because if you find the maximum clique, then you will find somewhere else the maximum independent set. So they are equivalent. And maximum vertex cover, least vertex cover is also you have seen. Oh yeah, I missed one property. So there is a connection between these two, which is if S is a vertex cover, then you can say something about S complement. What is that? Anybody else? What is V minus S in the same graph? Can there be an edge present in S complement? No, right? So which means that it's an independent set. So these two are also related. Vertex cover complement is actually an independent set. So which means that if you want to find the least vertex cover in a graph, you can as well do what? Maximum independent set, right? So this means that you are screwed. So least vertex cover algorithm is fast. Or let me just say they are equivalent. So least vertex cover problem is equivalent. So in the same graph, if you have computed least vertex cover, then you have computed maximum independent set and vice versa. These are equivalent problems. So finally, since time is up, finally this approximation of least approximate vertex cover, does it give anything for maximum independent set approximation? So you have a two-factor approximate vertex cover, right? Does it give anything for maximum independent set? It's not clear, right? Because there is a n minus which is happening. So then this in itself becomes a hard problem now. Approximate independent set is hard. So we don't know of any even this 2-factor, 3-factor, 100-factor approximation for the maximum independent set question. Okay, although for vertex cover you have a simple algorithm. Okay.